Hi everyone, my name is Nathan Rowe. I'm with Lidar News, and today I'm going to be reviewing a structured light scanner made by 3DMakerPro. It's called the Moose. It's intended for a consumer-grade audience, but it has impressive accuracy and resolution. The stated accuracy is 3/100ths of a millimeter, that's 30 microns, and the stated resolution is 7/100ths of a millimeter. So I'll scan a couple of objects. I'll scan this Raspberry Pi here, which doesn't look overly complicated, but it actually has a couple of interesting properties. It's quite bright, slightly reflective. It does have ports that have metal that is truly reflective. It has high contrast in areas, going from this bright white to some darker areas, and then it has many different recessed areas that are essentially kind of hollow. So we'll see how the scanner and software are able to handle that. We'll also scan this antler, which is larger. It is more irregular shaped. It has a lot of different textures on it and cracks and things like that. So we'll see how that performs as well. You'll also see a couple of objects in this video that come from the premium package. One being this tripod here, which is small but mighty. You'll also see this turntable, which is useful particularly for smaller objects like the Raspberry Pi here. And then it also comes with a travel case, which has a hard outside. Everything fits in there, and if you're traveling with this scanner, it would be nice to have. So we'll take a look at this. We'll see. I'll actually do a comparison of some measurements in JM Studio, which is the free software that comes with the Moose, and I'll compare it to measurements that I make on the actual Raspberry Pi here using calipers, and we'll see if that 3/100ths of a millimeter accuracy is an attainable level of accuracy for the types of projects that you might be doing. So let's jump in. To begin with, I think it'll be useful to discuss what structured light scanning is, and that will help us to understand in what areas the scanner performs well and in what other areas it has limitations. So you can see a blue LED light being emitted from the Moose scanner, and it's being projected onto a Raspberry Pi, which is a small computer that we'll look at in more detail coming up. What you can't tell about that blue light is there's actually a structure to it, and that's typically lines or grids. And when that light is projected onto a surface, it is deformed. If you were to project it onto a flat wall, there would basically be no deformation. But when you project it onto an uneven surface, that structure is curved or warped or distorted. Now the camera is observing the position of that structured light and comparing it to the expected position of the structure across that pattern. And by doing that and comparing the expected position of that structure and then the actual position of that structure, it's able to recreate the geometry of the object that it's scanning. And that allows you to create a point cloud, which you're seeing generated in green here. Okay, so let's take a look at the final model output. This is the mesh in JM Studio and comparing it to the actual Raspberry Pi. You can see there's a lot of detail here. This was processed with a resolution of 0.1 millimeters, and it's picking up the Raspberry Pi engraving pretty well. It does fuse the top engraving to that dark backdrop, which are actually separated from each other. But a lot of what we discuss here is kind of a mix of both the data collection but also the data processing, and I suspect that fusion is more to do with the data processing. You can see the engraving, the Canakit engraving up at the top, is recorded pretty well. You can read that quite clearly, and that's a very shallow engraving. It's very difficult to measure, but it's fractions of a millimeter. What you can also see is that there is a bit of a concentric ring pattern that's recorded in the geometry of this mesh, and I suspect that's to do with the reflective surface of the Canakit as well as the rotation when it was rotated on the turntable. And that is not a geometry that actually exists. It's barely noticeable. It has basically no depth in the model, but it does exist. Let's take a look at the lid of this case, and you can see in the mesh that the lid is fused to the body all the way around, whereas in the actual object there are just a few supports, and otherwise you're looking all the way through the case to the other side. So you can see that in the point cloud it actually did collect points related to some of these supports. It didn't collect them for all the supports, and that's just to do with the orientation of the Raspberry Pi and the scanner. So it's more to do with the processing that it fused the lid to the case all the way around. And with some more tinkering with the settings on the processing, it's possible you'd be able to separate these two. Now we're looking at the ports of the Raspberry Pi, and this brings up a classic issue with structured light scanners, which is reflective surfaces. So you can see on the Raspberry Pi there are these reflective metal surfaces, and they're not being well recorded in the model. So that's because structured light scanners are projecting this structured light, and the camera's trying to observe that structured light pattern, but on reflective surfaces, that structured light is either being reflected away or distorted, and it's not able to collect data in those areas. You can apply a matte spray to reduce the reflectivity of these areas, but I didn't want to apply the spray to this object. This side of the Raspberry Pi is pretty simple. You can see again the lid is being fused to the body. And on this side we have a micro SD port, and the mesh does a pretty good job of reflecting the geometry of that port. Let's take a look at the ports on this side of the Raspberry Pi. And you can see that the mesh does a decent job of collecting the geometry of these ports, but it brings up a couple areas where structured light scanners have limitations. And the first is similar to the lid that we were looking at, and that is that deep recesses and cavities are difficult to collect data on. And you need a direct line of sight, and that means that the orientation of your scanner and your object in these recessed areas needs to be just right to be able to collect data on that. Laser scanner might do a little bit better, but again, that also needs a direct line of sight, and so these are just difficult areas to collect data on. If we look at the texture map, you can see that some of these really shallow engravings that denote the different ports on this are picked up in the texture map a bit better. The mesh itself is not really discernible. You can't quite read the engravings on the kit. So it is useful to have the texture map, which records a bit of that information. Another challenge for structured light scanners is high contrast and issues with exposure. So as we've mentioned, a structured light scanner relies on a camera being able to observe a structured light pattern on the object. Now when you have really high contrast, some areas might be overexposed and the structured light pattern is blown out in those areas. And in other areas where it's underexposed, there might not be enough reflectivity of the structured light pattern for the camera to be able to observe it. And in those areas, either erroneous or no data is going to be collected. So you can see in the point cloud, there was no data collected in those ports. And I suspect that some of that is actually to do with contrast, because there is a bit of some features that could have been scanned in there, and I believe that the scanner did have the orientation to be able to reach those. Despite no data being collected in those areas, you can see that the processing has the tendency to want to enclose this object and not have holes in it. And that's despite me not selecting the repair gaps feature in the processing of the data. Now, I didn't tinker around too much, and it's possible that you can find some settings that will allow you to not close these gaps that exist. You're seeing more with these holes on the bottom of the Raspberry Pi. And again, the processing is wanting to close that up, even though those are true voids that go down throughout the entire case. All right, so now we're going to take a look at the accuracy of this model and see if it's actually accurate down to 30 microns as advertised. So here's the Raspberry Pi in JM Studio again, and I'm going to begin taking measurements on this Raspberry Pi in JM Studio as well as on the actual Raspberry Pi with a pair of calipers that are accurate to 2/100ths of a millimeter. So taking measurements in JM Studio is easy. You can see it being done on the left Whether or not the line that I've drawn here is perfectly orthogonal to this case is up for debate, and the same can be said with the calipers that I'm using on the right. And that makes a difference when you're getting down to accuracies of 0.03 of a millimeter. So you can see the accuracy, or excuse me, the width on the Raspberry Pi in JM Studio is 62.65 millimeters, and the width in using the calipers is 62.61 millimeters. That's a difference of 0.04 of a millimeter, very close to the advertised 0.03 of a millimeter. And with this simple test, it's not a perfect test, but I would say that the accuracy that's reported is attainable. I would think that you can get sub-tenth of a millimeter accuracy using the moose. Okay, so we're going to shift gears and scan a different object. This is a deer antler. It is a shed. No animals were harmed during the filming of this video. And it has a couple different properties that I think will be interesting to contrast to the Raspberry Pi. It's larger. It is not shiny or reflective. The Raspberry Pi had the metal reflective surfaces, and also the case itself, which is kind of a white, shiny, reflective surface. So this is much more matte. This is also much more irregular shaped, whereas the Raspberry Pi was very dimensional and orthogonal. This also has a lot of surface texture to it, and it's hard to see in the video right now, but you'll see in the model coming up that across the entirety of it, it has a lot of kind of topography and undulations. So let's take a look at how this scans. I want to highlight why working with a larger and more irregular object like this antler is a bit different than scanning something like the Raspberry Pi. So you can see I'm attempting to use the table scan approach, and I have the antler mounted on the turntable, the scanner mounted on a tripod, and in the screen above there is an area in green, and that's the area that the moose scanner is collecting data on. You can see the tines of the antler passing through the camera view, but they're not green and there's no data being collected on those points. And that's because the working range of the moose scanner is fairly restrictive. It's advertised as being 150 to 400 millimeters, but in JM Studio it states that it prefers to be 250 to 300 millimeters away from the object. And that's a span of 10 centimeters at 25 to 35 centimeters away. And it takes a bit of practice to keep your scanner the proper distance from the object to collect the data on the areas that you're hoping to collect data on. Here I'm using the hand scanning approach, and you can see that I'm trying to find the right distance to be from the antler. And once I find that, and you can see in the green that I'm covering a lot of the antler there, I'm trying to maintain that same distance somewhere between 25 and 35 centimeters away and follow the shape of the antler. And it's difficult to see, but on the left side of the screen, JM Studio is showing a distribution of the points and whether I'm too close or too far away. So you're trying to look at that, determine if you're too close or too far away, and follow the shape of your object. Now it's important to maintain a nice smooth scan over the object, and that provides the continuity for JM Studio to be able to track the relationship between all these points to each other. If you move very abruptly and all of a sudden are scanning a different section without continuity between it, it loses tracking and tells you to go back to an area that's already been scanned. So you can see I'm moving around, covering a lot of area, and this prevents me from having to set my tripod up a whole bunch of times and do lots of rotations on the turntable. So for an object like this, this is definitely the preferred approach to scan. Here you see the point cloud that was generated from that hand scan, and you can see it covered much more of the antler than the table scan approach. And this would be one of several different scans that I would take, and once you start taking multiple scans and merging them together, you can see how complete your model is and determine other areas that you need to get better coverage of. Okay, so here's the model that I generated for this antler, and this is at 1/10 of a millimeter resolution. You can see it's very detailed. It does have some gaps. Those are the areas in green where it's not fully enclosed. And with more scans, I do believe that I could close that all in. The tines did prove difficult, and it really has to do with the ability of the software to track. And when you're up at the top of those tines, And because of the working range of the scanner, there's just not much for the software to grab onto and track. And so it starts to get a little lost up there. And so it is a little bit difficult to get those tines completely covered. But I do believe that that could be done. You can see super detailed texture here, including cracks that are on the antler. It almost has more detail than what you easily see with your eye because of just the way that the lighting and things in the software work. So I really think that this is a very impressive scan. I will note that the resolution of your scan is a bit of a trade-off. The higher resolution that you go, the more holes that you'll get. And you can see I have a fair number of holes here. And if you bump down the resolution, you start to get better coverage of those holes. And you can use some other aspects of the software, like filling holes, which does a bit of extrapolation. And I was just interested to see what it was actually collecting. Here you can see the texture map of this antler. And you can see it does a great job showing the cracks and various features of this antler. I did notice that both for the Raspberry Pi and for this antler, the color was a little bit off, but I didn't make any effort to balance that color. All right, final thoughts. I think the Moose scanner performed quite well. Really impressed with the accuracy. I think it just highlights the advantage of structured light for these types of applications. You know, it's much more affordable than a comparable laser scanner would cost for the type of accuracy that we're seeing here. It doesn't require expensive timing components and things like that. So really cool technology. The accuracy was impressive. JM Studio, which is free software and it comes with free upgrades for life, I thought worked pretty well. It has a little bit of a learning curve. The Moose has a little bit of a learning curve, and it takes a bit to figure out that distance and figure out when to use a table scan, when to use a hand scan. And in some situations, I actually combined the two of them. I would do some table scans and then fill in the gaps with some hand scans. So it takes a little bit to figure it out. The more scans that you're merging together, the more room there is for needing to use manual merging and things like that. And I didn't go into all the different details, but I hope this gave you an overall idea of what the Moose is capable of, its accuracy, what you can expect a final product to come out like, and hopefully it will be appropriate for some of the projects that you have going on. Thanks.